All right, ladies and gentlemen, welcome back to another video with Mr. Kenton. Today, what I'm going to be looking at is solving a problem that has to deal with looking at rates of reaction, specifically using the stoichiometry component of a reaction to help you set up and calculate for the reaction rate. Here are the two questions. They're in the text. They're actually the sample exercises that have been listed there. But I wanted to do those because it's something that you have reference to. Obviously, you can look at how they explain it, but then you're also going to be able to watch with me and see how I go through and solve this particular problem. So hopefully you'll find that insightful and so it's something you come back to. All right. So let's just read the questions and then let's talk through how we would go through and solve it. So the question states, how is the rate of disappearance of ozone related to the rate of appearance of oxygen in the following equation? So we got 2 moles of ozone decomposing or breaking down into 3 moles of oxygen. Okay, so that's question number 1. And then question number 2 is if the rate of appearance of O2, delta O2, change in concentration of O2 with respect to time is 6.0 times 10 to the negative 5th molar per second at a particular instant, what is the value of the rate of disappearance of ozone, so the change in concentration of ozone divided by the change in time, at the same time period? All right, so 2 questions, one very conceptual in nature, the second one looking at how do we take that concept that we're going to be solving for in part A, how do we apply that information and get out a numerical value in part B. Okay, so those are the 2 questions we're going to be looking at. And so what I'm going to be doing is I'm going to be opening up a new document. So what I'm going to have to do is I'm going to have to open up or clear this one and go to another one, right? And so let's just deal with the first one. They give us the stoichiometry and they want us to write a rate and show the relationship between ozone and oxygen. So if you remember, the equation they gave us was 2O3 gas goes to 3O2 gas, right? And so if you remember from the PowerPoint, we talked about how if we're given the stoichiometry of a reaction, something like this, and they're asking us about the rates and how we compare them, remember we can say that the rate is equal to 1 over the coefficient, we'll just say that's A, times the change in concentration of, in this case, it'd be O3 with respect to time, and it's going to be negative, is going to equal 1 over, in this case, we'll say B, in reference to the coefficient for oxygen, times the change in concentration of oxygen with respect to time, right? And so if we wanted to take that and write the rates with respect to those coefficients, we just simply have that the rate is equal to negative 1/2 the change in concentration of ozone divided by delta T equals 1/3 times the change in concentration of oxygen with respect to time. Okay, and for part A, that's really all they're asking you for. They're wanting to know what's the rate of the reaction and how they're related to each other. So now that we have both of these rates right here, we're going to be able to use that to help us approach and solve part B of our question, right? And so to do that, let me go ahead and clear that. And so again, so this is for question B, and we're going to need those rates. So we're going to write those rate equals negative 1/3 the change in concentration of ozone with respect to time equals 1/2. Oh, whoops, I flipped them. So it's negative 1/2, and then it's 1/3 the change in concentration of oxygen with respect to time, right? And in part B of the question, they told us the rate of oxygen. They said that the rate of oxygen, so the rate of oxygen is equal to, it was 6.0 times 10 to the negative 5th molar per second, right? Okay, and so when we think about that, that's our rate of oxygen. And so if we wanted to look at it from this perspective, they want us to find the rate of ozone. And so in order to do that, we're going to need to rearrange our equation so that we can get it with respect to ozone specifically. So if we think about this, what we're saying is we essentially want it to be represented as we got negative 1/2 change in concentration of ozone with respect to time equals 1/3 the change in concentration of oxygen with respect to time. Now, essentially what we want is we want to get this component by itself. And so in order to do that, what we would need to do is to multiply both sides of this expression by 2, right? So I'm just going to put giant parenthesis here. We're going to multiply everything by 2. Now, when we do that, the negative 1/2 is going to be converted to a negative 1, right? So that's just a negative 1. And then this is going to change, right? So now we can kind of come down to the bottom that we're going to have negative the change in concentration of ozone with respect to time, to the change in time, is going to be equal to 2/3 times the change in concentration of O2 with respect to time. Okay, and this is where that rate that they gave us is going to come into play, right? Because what we're going to do is we're going to plug in that rate right here, because this is telling us the rate of change of oxygen is 6.0 times 10 to the negative 5th molar per second. So now we've got this set up. It's going to be 2/3 times 6.0 times 10 to the negative 5th, right? And so then 2/3 of 6, like we can ignore the 10 to the negative 5th for now, 2/3 of 6 is 4. So that means that the rate of O3, so the negative delta of change in concentration of ozone with respect to time, is going to be equal to 4.0 times 10 to the negative 5th molar per second. All right. And the only thing that we could communicate, we could certainly, if we wanted to make it positive, we could distribute that negative sign so that it's communicating that disappearance. But if we leave the negative over here, we're still communicating to ourselves and to each other that the rate of disappearance of ozone would be 4.0 times 10 to the negative 5th molarity per second. Now, last thing before I kind of end this video, guys, just to consider, if we're looking at it from the stoichiometry perspective, right, the rate of ozone should be smaller than the rate of oxygen based on our understanding of the stoichiometry. It was 2 to 3, so for every 2 moles of ozone that decomposes, 3 moles of oxygen is being produced. And so that means the rate of disappearance should be less than the rate of appearance of oxygen, just simply based on the stoichiometry. And so our numbers reflect that. And so this is our final answer right here, and it should make sense to us. Okay. I hope this has been helpful. Hope this is useful. Take the time to watch it. Feel free that if you need to, when you're watching the video, pause it. If you get stuck, rewatch something. And if that doesn't help, ask me a question. Come see me during office hours. I'd love to help you guys out. Thank you so much, and I'll see you guys soon.